Good afternoon, everyone. Hope everyone is doing good. Uh, I decided to create this video lecture on giving you an overview about system Verilog. The other day, I was chit-chatting with the students, engineering students at one of the very big university in Canada, prestigious university, and they seem to have no idea what it is. And so the traditional educational system, what it is, the knowledge about the bookish knowledge, and they are more concerned with giving the fundamental about what AND gate does, what NAND gate does. But when time comes for system level, SOC level, things become complex. Even at individual IP level, it's a quite tricky thing to verify uh, in practice. Uh, it's very important. Think about that you're gonna buy a cell phone and cell phone IC breaks. You find the bugs in that. Would you like to buy that? No, absolutely no. So what engineers do, they try their best to capture all bugs, but in theory it is very difficult, almost uh, close to impossible, you may say. Think about for a second, if you want to verify the whole address space of 64-bit processor, think about 64 lines, and each line can have 1 or 0 value. So how many combinations it would be? 2 to the power 64, an enormous number. So that's that many test cases you would need if you want to verify each combination. In reality, it is not possible. But that was just a simple, giving you some sort of idea. System Verilog, um, it is a language whose main emphasis is on hardware verification, um, utilizing the random, constraint random verification approach. It has object-oriented features. Also, you may write assertions. Assertions are de facto practice nowadays in hardware industry, in chip design. So it becomes a very important language for verification. So let's say in this lecture we're going to have a quick overview. Quick overview in the sense that you don't have to APPROACH. You just stick to basic fundamental principles, and then you can expand your design. You can make it as big as you want. But if you have some basic idea what it is, you will be more confident. So many people think about system Verilog like a big giant, like so you guys might have heard about this story, blind men and elephant. So somebody touches elephant's teeth, it thinks that okay, elephant is like that. If somebody touches its tail, he says that okay, elephant is like a rope and whatnot. I mean, in practice, I mean, if you want to go full whole language features and full language manual, it's an enormous giant. But don't be afraid. We're gonna deal step by step what it is. If we know a conceptual overview, then you can expand your understanding and write complex test benches and whatnot you can do. So let's say, put simply, what functional verification is. So functional verification means that you write some programs and you run some software, simulation software, to make sure that your device under test or your DUT operates as intended before manufacturing. For example, if you ship out your chip design data to manufacturing and it has a lot of bugs, you spent a lot of money, billions of dollars, and at the end you get this buggy chip which has a lot of functional errors, functional bugs, I would say. Error and bug, there is a considerable difference, but we are not gonna discuss here. The bugs are very difficult to find, you know. I mean, your chip may work while it has bugs, you know, but it will only be impacted if you exercise that corner case, um, which brings that bug out. So it becomes very important that we verify, or we try to capture as many as bugs before we ship out our data to manufacturing. Simply, it's very simply that we want to, you know, improve our design, less functional errors, because there are a lot many other places where chip can go faulty. Okay, think about almost 60% effort of chip development goes to verification, and functional verification is large. The verification includes your functional verification, physical verification, testing, and whatnot. So out of that whole chunk, your functional verification has a huge chunk. And nowadays, in a typical SoC, I mean, if we say typical SoC, what components you will have? You would have somewhere, you know, let's say if you have this full SoC, you have bunch of, you know, peripherals here. You have system bus, you have another, you know, peripheral bus, you have processing unit, or I may call it CPU, right? You may have GPU, you may have memory element here, and bunch of peripherals, USB and whatnot, all are connected. Think about, to verify this whole system, it's a very complex task. And then if your bus is 64-bit, how we can make sure that, you know, every combination we have exercised. So it make more sense if we, you know, if our input is stimulus to the chip or the IP under verification, it has a random pattern. We can maximize our coverage. Well, put simply, coverage means that out of say 100 test cases, how many test cases you have verified, or how many cases you have verified. So coverage may, you know, you can put a saying, say coverage, you can define functional coverage, code coverage, and whatnot, different kinds of coverage. But the basic idea for the coverage is that your verification environment has exercised how much portion of your chip, how much functionality of your chip. Okay. Another important consideration here, the reusing, you know, like in software, we reuse the libraries. In the same way, can be reused the already developed code. Say an engineer or a team of engineers, they have developed verification code for one chip, and they spent 2 to 3 years, and then next version of the chip, we have only light modification. Can we reuse it? Think about it. Or is there any way we can make use of already written code? We don't have to write again and again. That will save a lot of time and a lot of money too, because we don't have to pay extra money to engineers for verifying those pieces of writing code which has already been written. Okay. Now think about, what if we can change the stimulus randomly at runtime before applying to duty, right? So let's say if you have duty here, what if just before applying, your input might be coming from peripherals, from memory, from whatnot, and just before applying this input, you are able to change randomly. Okay, that will give you better access to finding the bugs. Okay, or can we improve our functional coverage, right? So all those things lead us to find a way to do things in a better way. Typical hardware design languages, say VHDL or Verilog, those are very good when you want to write a piece of code which a synthesized tool is able to do synthesis for it. Okay, it's very good. But for verification, you need some extra features. Say for example, you need a factory, object factory, which can generate different kind of objects, right? Objects here may be a stimulus, and that objects based on certain parameters are randomly configured and driving a stimulus to your DUT. Okay, think about it. So all those features, we need that to to optimize our verification effort. The question comes that what is the language? So system Verilog, one name comes, then another name comes Specman E. Specman E based verification also has the random constraint random approach, but we're not going to discuss it here. We will stick our discussion to a quick overview on system Verilog. All right. Okay. In a typical verification environment, we use a layered approach. What it means? It means that, say for example, you guys have a chip. It's a complex project, and you want to verify it. So what happens? A bunch of engineers, maybe your project leader, yourself, they get together and they draw some plan on Blackboard. Okay, they discuss that we will have a verification top component which will control all our environment, and then we will have an individual test, means that what functionality we want to test, and some kind of a scoreboarding system. Here we say watchdog that will maintain whether what was the result of the test, pass, fail, and certain other information, whether test exit out. It becomes important when we are using randomized approach for giving a stimulus. Maybe that particular randomized input makes system hang, so we don't want our system to hang forever. So watchdog timer, here there is a timer in this whole in this module, as well as the scoreboarding features that will keep track of the time, and when the time elapses, it will kill that particular stimulus which is causing problem. And so we can revisit what stimulus caused the problem, and we can fix the bug in the system. And all these components then in the end are connected to the test bench, right? And in the test bench we can have individual agents, or we can make one more layer, agent plus some other components clubbed together into a component which drives stimulus to the chip. And in a typical chip you would have PCI Express, okay, connectivity, bus connectivity, Ethernet components. So this is just a example. You may have more components associated in this whole system, and then we can draw a line here which separates our HDL, hardware description language, versus our system Verilog verification environment. Okay, so HDLs are good when you wanna design the chip, but those are not very good when you want to verify. For verification, we need extra features as I was just discussing a minute ago, right? So this is a typical sort of very basic theoretical model for verification environment. When you discuss among your team members, and then you're gonna decide what we need, which module, who gonna develop it. Okay. Now let's draw our attention to the component class. So here, say PCI Express component class, right? So we can write a generic component class, and then based on the parameters we can modify whether it is PCI Express component or Ethernet component, right? So we can make a general class, the component class. So it will have, it's again layered, different layers. So it's like onion, you make more layers till to basically abstract out things. So it goes back more into abstraction. I discussed abstraction in one other video. I think it's under algorithm video series. If you haven't watched that, I would encourage you to watch that video where I explain why do we need abstraction. So it is similar way, the abstraction what we use in software industry, or when we develop software. The similar kind of abstraction, we are trying to represent the same information at a different level, different hierarchical level. So here in the component class we have generator, checker. Generator job is to generate packets, say for example, or objects or different things. And then the checker will check, okay, I have generated this stimulus, I expect this output, and what output I got from the chip, and yes and no sort of thing, whether I match with the expected output or not. Okay. Then we have here next layer. So this is a transaction layer at a very high level layer, transaction layer. So it means that, okay, drive X to the chip. So that becomes your one transaction, for example. But how you're going to drive it, that agent will decide how you're going to drive it. So we have the agent layer, and then agent knows, okay, I'm going to drive this, but how? Then we need a connection. So we need a connection layer. Okay, and connection layer are connected via virtual interfaces to the chip. Virtual interfaces here means that it's not, its interface is configured at runtime. Okay, so that you have more flexibility and reusability of the code. Okay, so at the transaction layer we have, say, very simple generator, checker, and a transaction. Okay, simple transaction, say write register. Okay, so processor is executing command write register for connectivity test. So that becomes your transaction. Okay, how this transaction is gonna be working, then there is a generator agent. Okay, agent layer. So in the agent layer you have generator and you have checker. Generator agent will give input to the BFM agent, bus functional module agent, driver agent, and monitor agent. These are part how these are interconnected. That becomes how you design the test bench. So every company, they have their own internal mechanism system for the test benches. But here the idea is to give a basic overview, basic theoretical background about test bench and different components, layer, test bench approach and all. Okay, and then you have this connection layer where BFM layer, bus functional module layer, driver layer, monitor layer, these are clubbed together, makes one connection. Okay, so that's a basic layered approach for test bench. Hope it makes sense. Think about it. Typically these things are not being taught at university. because it is more to do with the practical in your industrial work. The concept of the test bench and all, it's good enough for a tutorial, okay, not as a full length course, but it's good to have the idea about how you're gonna develop it if you wanna be in industry as working as a verification engineer. Okay. Now here, what I'm trying to show in this diagram is that a test, say you have a test that verify this functionality, whether you are able to read and write at that particular memory's address space. Okay. So test may have multiple test components, and those tests are typically check some specific functionality of the chip, say boot up sequence, for example, power on boot up sequence, right? Or say how to handle interrupts, you know, those sort of things, um, or say security, check for the security, you know. Say this transaction is let's say if your chip is implementing a security module, so you may want to test whether it really works or not. So you may design a test which is like breaking that security, and want to test whether I was able to break it or not, how good it is. And we have typically, you know, in a randomized approach, the packet test, packet approach. So we send the different packets. Packet means, you know, you club together the stimulus into a, you know, whole stimulus stream into chunk of packets, and then you are driving those packets to the chip or device under test. So let's say from the test it starts, you communicate with the test packet test component, there is a generator communicates with the driver, and driver is driving the stimulus to the chip. Okay. And then the stimulus from the chip, the output of the chip, is monitored by monitor module, right? The monitor module communicates with the checker, which keeps track of this stimulus is being compared, what was the result, what was not the result, and so on. So basically, the verification idea is very simple. Your DUT, okay, now you derive some input and you get some output. Okay. Now how will you check whether this is the expected output? So you should have somewhere in your test bench that whatever is the DUT is doing, you have the similar module which is mimicking that, it is behaving like a DUT or like a IP under test, and then this is also generating the output, and then here you are comparing the output from the chip. Okay. And output from your internal module, which you have written functional module. Okay. Same stimulus is going to both of them, and that will tell you whether this test was passed or not. So that's a very simple idea, but here we are putting this very simple idea in a system Verilog or test bench framework. Okay, so got very basic idea about functional verification. Good. Let's go a bit more in detail. Say for example AUART, universal asynchronous transceiver receiver, UART example. So we have verification top, the environment, you know, it controls everything in the verification environment, the top component. Then we have this test bench component, it has Ethernet interface, PCI interface, UART interface, different interfaces. It is communicating with the chip or your device under test. Now, once you are testing say one functionality, but in real world scenario, you might have some random stimulus as well. So for those random stimulus, you have something called Ethernet iterator, means that component is continuously sending some data to the Ethernet, but you want to test UART, okay, UART test component. So you are sending stimulus via UART test component to UART interface. However, Ethernet and PCI are also working simultaneously, so that you're kind of trying to simulate the real chip environment. Okay, so these Ethernet and PCI Express are acting as a background noise generator. And here you have your test. Okay, so test is communicating with all these components, and you have here your watchdog timers for scoreboarding and timing purposes, timer purposes, and this completes your verification environment. Okay, now all those individual components, you can make use of object-oriented programming approach, and you can develop these components in system Verilog in an easy way, and then connect all these pieces together and good to go. Not very difficult. Good. So let's talk further. In this diagram, what I'm trying to show is that the interaction between your different test bench top level components. So you have verification top. Now verification top, okay, you might have one a block which creates the objects. Okay, that objects interact with your test, watchdog and test bench components, and build and configure. Here you are basically doing the randomization, right? So let's say your stimulus generator needs a 16-bit of data. Okay, so you can randomize the data, 16-bit, whether it will be 101 or 0101. You can randomize the sequence. Okay, so after initial setup, initial configuration, you start the watchdog. Okay, and then you basically, at this time your chip is in reset. After you have started your basic components, then you deassert the reset. Okay, or you start your chip and start writing to the hardware. Now your main test is running, right? Now you wait till your main test completes, and then there would be some component to put the result in a report format in your verification environment, and then finally some failure paths or timeout paths, means failure paths that for those stimulus your system hanged up, right? So that you can go further and debug those things. So this sort of a very basic overview about the verification environment and how the different components are connecting together. Sounds good. Hope this gives you a very good idea about functional verification. Now remember, here these examples I'm talking about the real world example as you do in the industry. Now this is a conceptual idea about hardware verification as it is done in industry. You may modify based on your requirements or based on your company's requirement. You may modify, but basic idea is this way, that you create objects. You create here, you have the object factory which is creating different objects, different kind of objects. Think about brick, right? So it's a factory of the brick. Now brick may have different sizes, right? Different kinds of bricks. So different kind of objects you are generating basically, and then you are configuring those objects to have different properties, maybe blue color brick, red color brick. Basically trying to say that you are randomizing, right? So when you randomize, you kind of improve your coverage, you exercise more and more data points in your input space. And then you basically start or deassert the reset for your chip and start writing to your hardware, and your test is running, whatever test you are doing, and then some way to store the results or to report out the results in a report format, and then timeout paths, okay, so that you can go further and analyze, right. Here somewhere you will also write a coverage component, but that coverage component is language provides the facility. You can embed those things in your class when you're gonna write the class, so easy that way, okay. So don't afraid, it's very easy, Now let's say, now we turn our focus on into system Verilog. What system Verilog offers? So in any language, always remember, any language is very simple. There are three components of any language. First is approach. What this language, what is its approach, whether it's object oriented, whether it's just purely sequential, there is nothing object sort of thing, or it's a including whether this language is giving me parallelization features, or giving me approach for, say, there are some languages like Prolog and Lisp, they provide me features for which are very useful for if I want to program for a robot, for example. Same way, system Verilog, it has its own features. So basic data types, what kind of data types language supports. Second is control structures, looping constructs, and third thing is the reporting thing, or basically semantics of the language. Three major important things. If those three things you have in mind, then any language you can basically work with. So system Verilog, it offers different kinds of data types. Two states. So two states means 0 and 1, right? So what we'll have, these will have less memory requirement, better performance, reduced memory, say bit, integer, int. So it has two kind of integers. So one is int and one is integer. So integer is actually 4 state, int is 2 state, byte 2 states, short int 2 state, long int real, okay. Time is 4 state, okay. 4 state will need more memory. Now it has queues, dynamic and associative arrays. So queues, it's an important feature, queues. You don't have to write your own linked list, you can just use built-in queue of the system Verilog. Isn't it interesting? And that is faster, and built-in support for sorting and searching, okay. You have unpacked arrays, packed arrays, okay. Packed arrays, packed arrays. There is a slight difference where when to use packed arrays, when not to use, when to use unpacked arrays, but those are fine details, we can look into it too. How we can write, say for example, queue. So this is a typical syntax queue. As long as you put something, as soon as you put a $sign in between square brackets, it turns out to be the queue, okay. So that's a syntax. For dynamic arrays, you don't put any number between the square brackets, okay. What it means that you have to, when you want to use the dynamic array, you have to define its size. Say I want to use dynamic array, so what I'm gonna do, I define the dynamic array A, and then I'm gonna use new. New is the command or keyword which allocates the memory for locations of this A array. If it is a dynamic array, you have already declared. With the queues, the new or allocation of the memory is done automatically. You don't have to worry about it. Queues are very powerful. Remember that. Remember to use queues in system Verilog. And easy operations, push front, push back, those sort of things you can make use of. If you want to empty the queue, delete the queue, you just queue and then equal to curly braces, nothing in the curly braces, it will delete the whole queue. Isn't it fascinating? Interesting. Always remember queue, very important data type. Make your life very easy. Another thing, classes and structures. So classes and structures, the people who are coming from computer science background, they might have learned these things again and again, classes and structures. So basically these are the abstraction mechanism. In simple sense, say human beings, you can make a class, right? And then you can make a subclass or child class, say men and women. So that sort of thing. Think about nouns as a class. Okay. Now here, how did we do that? We defined this struct, a structure. A structure is also like a class, but in class you can have private and public members. In a structure you have just one type, everybody can access those members. But you are organizing your data. So like for example here, I want to define a pixel, okay, and a pixel can have RGB, 8-bit, 8-bit for red, 8-bit for green, 8-bit for blue. So what I can do, I can make a new type, pixel underscore s, make it a struct, and when I want to use, now I just want to use, I will just use pixel. Pixel becomes my new data type and I abstract it. Okay, easy. Unions and packed arrays. So unions and packed arrays is simple, facility of having multiple views of the same data. Let's say union. What union will do, in the structure, is when you define the structure, it will reserve the memory space for each 8 bits for each R, G, B and R, G and B. But in union you can have different kind of data with a less memory requirement. So what will happen if you define say int IA and real RA as a union, so whichever is the bigger, it will reserve the memory space for that, and the binding happens at the runtime. Okay. Now let's talk about strings. Very powerful feature in system Verilog, especially for verification purpose when you want to print out different messages and all. Say for example, you can define a string s, and s, what s contains? S contains LEPROFESSEUR, leprofesseur.org. Easy. Now you can print s, if you want to print s, just call, okay, write s, and then string operations, searching, sorting, finding a word in the string are easy. Inbuilt support for a string. Numerator types. Okay, numerator types, easy understanding of the code and debugging help. Okay, you might have seen, say for example, you want to define color and you have only 3 options, red, green and blue. So you can basically define a new type, numerator type, and you can call it a color, and which will have value either red, either green or either blue. That's it. So it's a facility for defining your own type, which can have specified values. So these are basic data types. Queues, strings are kind of you would use more when you are doing verification, and I think I haven't discussed here logic type. So logic type are similar to register and wire. The difference is that your register or your wire can be driven by multiple nets. But here, say if you want to find out the bugs in the net list, whether the signal is driven by multiple drivers, what you can do, instead of using a wire, you use a logic, and your simulator will print out the error message, because logic type cannot be driven by multiple drivers. Okay. Now, simple routines, what system Verilog offers. So, system Verilog, you can write the tasks, you can write functions, or you can write void functions. Say you have a bigger computation, bunch of things, you want to write a code and it doesn't return a value. Okay, so either you make it a task or you make it a void function. Void function are similar to tasks. However, void function, they don't return a value, right? And they take the input argument. The example for the task, say task do something, you are printing something here, display LEPROFESSEUR. Another important feature of the task is that you can have delays. You cannot have delays in the functions. Functions are executed instantly, but in task you can have delays. So you want to have some delay of 100 units. A unit will depend on how you define in your test bench. So 100 units delay, typically it's picosecond, but it depends. You may change it via time scale description or via some other meaning depending upon your test bench environment. But let's say you have 100 unit delay, then you want to, after printing LEPROFESSEUR, then you want to print LEPROFESSEUR.arg, and then after some delay you want to print I love LEPROFESSEUR, and then you want to return. So this becomes a task. Okay, for the function, function must have a return. Okay, it is must for a function that it should return a value. Otherwise, these functions are very similar, like you have used the functions in other programming languages. Okay, void functions are similar to functions. Again, they don't return, they don't need to return, or they don't return actually any value. So where do we use tasks and where do we use void functions? Say if you have delay in your task, in your basically program, then make use of task. If you do not have a delay and you do not want to return any value, then you can use a void function. Okay, clear? Simple. Interfaces. Now you have everything and you want to connect those pieces together. So interfaces here are a powerful feature of system Verilog. Okay, think about, these are intelligent bundles of wires. Okay, not only they connect, but they may have more information about the connection. Okay, and also, in a regular Verilog, if you want to say you have a bus, okay, 8 down to 10, so you want to basically connect individual signal to individual signal between two blocks. So let's say you have block A and you have block B, and you have actually bunch of signals, 10, 20 signals. Okay, so you have to individually connect all these signals. But in system Verilog via interfaces, you can basically make a bundle of it, and just in one line you can connect between A to B. Okay, say for example here we have defined bus interface. Okay, its input are bit clock, right, and it has logic grant request, logic reset. So say we have more information other than connectivity with this interface. Okay, and how we are using, we have defined bus interface and we just connected to bus interface dot dot and bus interface. Okay, the dot notation that we want to connect this instance of this bus interface with the dot, and that's it. So instead of writing 10 lines, we just did write one line and get away with it. and it ensures that you don't spend your time, okay, I forgot this connection, I forgot this connection. You just change at one place. Now another powerful feature of interfaces is that mode port. Okay, mode port means that the orientation of the connection, whether to in to the DUT or out from the DUT. Let's say the same bus interface will act differently onto the when it's going to connect to your test bench, but when this interface is going to connect to DUT, it will act differently. But you can club all these things together in one interface. You don't have to write again and again. So when it's going to connect to the test, the request and reset are going to output from the test bench, and input to the test bench would be grant and clock. Other way around, onto the DUT, input to the DUT would be request, reset and clock. Clock is the output from test going input to the DUT. Okay, and what is coming out from the DUT is the grant, which becomes input to your test. Simple. So mode port, right? Powerful feature of system Verilog. Basically it is making enable you to write less code. When you have less code, you would have less bug in your own test bench code. Think about, you are finding the bugs in the RTL code, right, and you are writing test bench code. Think about, if test bench code itself has more bugs, how you going to verify it? So the idea is that you write less code and do more, right? So that's the basic idea here. Okay. And if you want to call in same, now we can define the module bus, and this example here shows that how you can assess the signals from an interface with the dot operator. Okay, so let's see, if you want to assess the clock signal, do you want to wait on clock signal passes? So what you do, bus if, that is the interface, dot clock at the rate pass edge. Good, very simple, don't be afraid. Basic object oriented programming, class and object. Object is nothing but an instance of a class. Class is thinking in terms of nouns, becomes a class. Say transaction becomes a class, and what is in the transaction? You have the address, you have error, you have data, you have functions. You can define functions in the class. You can define bunch of things. Now when you have defined bunch of things, how you can create an object? It's just simply, object is the instance of class, like you call int a, same way you call transaction trans. A trans becomes the object of the class transaction. But before using any object, we need to give memory space for this object, where this object gonna keep its own data. So we use it via new. New keyword allocates the storage or the memory area for this trans object. Okay, fine. When you want to delete, you can just say trans null. Okay, and then you can write a task. Say, let's say you want to write a gen task. Okay, so this gen task means that it is generating a transaction. Okay, you basically make a transaction object via new. So first you basically write transaction, and then T, what it does, that T is a type of object which has a type of transaction, that is your class. As soon as you write T equal to new, means that now T has the space in the memory allocated to T, and now you just call transmit function to transmit this particular object. So you're not transferring the class, you are transmitting the object. So you are working with the objects, right? So you are not, say, going back to the example of the factory. So factory is there, class is there, which is is there for you to have different objects. So factory is producing a brick, brick becomes your object. Now you can throw that brick can be, may have blue color, brick may have red color, right? Or let's say I say this is a factory, okay. So this is equivalent to your class. Okay, now this is generating individual bricks. Now you can apply methods on individual bricks. Bricks becomes your objects. Good, easy. I think it's difficult here. Now let's say randomization. So where we can do randomization. As we discussed, we can randomize the data packet, say 8-bit bus. We can randomize what is data we are giving. We can randomize device configurations, we can randomize environment configurations, we can randomize primary input data, we can randomize the encapsulated input data, we can randomize protocol exceptions, we can randomize delays, we can randomize transaction status, we can randomize errors and violations. Now let's say here, so I'm writing class packet extends basic packet. So we are using inheritance feature here, base packet. So this class packet, it's like a child is inheriting property from the base packet. Okay. Now as soon as you write the rand, when the simulation will run, it will try to randomize these data items, source destination data. Okay, and since you are randomizing it, you have to write the constraints, otherwise the solver doesn't know, I mean, what is the limit, you're gonna it will basically go its whatever is the defined limit, high and up to low, which may be enormous. So it's always better idea to write constraints as soon as you use the rand keyword. So let's say you write the constraint that your SRC can have value greater than 10 and less than 15. So whatever packets would be generated, these will be generated in between source value 10 to 15. Okay, and you are done. Now when you want to use, you can use packet P, and when you write packet P equal to new, it will give the space in the memory. It's equivalent to malloc. If you might have did in C, there was a malloc for memory storage. Same way here we are using new, or it's equivalent to C++ new, same way. Now assert p dot randomize. So as soon as you do, you have invoked the randomize method on object P, it will give you a randomized, it will generate a object with a random value of SRC in between 10, 15 and other random, say, randomized data value as well. Assert is the assertion. What if your randomization fails? That will give you the error if randomization fails. So assert is, we are writing an assertion. It's a good practice to write assertions when you do randomization, because not every time you get a randomized packet. So you will come to know that, okay, for this kind of scenario I did not get randomized packet and it's been recorded you can read the report. Easy. Another important piece in system Verilog was the coverage. Remember, we were talking about the coverage. It helps to get better coverage. So what we can do in each class, you have, say, data randomize, port randomize. You are using the random keyword onto that. In the same class, you can also define a cover group and cover point. So when you define cover group and cover point, this basically stores the statistics about different items which you are randomizing in bins. Okay, and those bins you can analyze later on about the statistics, how much it's been able to cover, what not. Okay, like you have new keyword for getting reserving the space for the object in the memory. Same way you reserve the space for cover group in the memory. Okay, easy. Assertions. Assertion is another important feature. Assertions make sure that that your intention is validated, it is behaving as it is intended. For example, there can be different kind of assertions. Immediate assertions means that A is equal to B. So as long as it is true, it will not give any warning or anything. But if for certain stimulus A is not equal to B, it means that this condition is not being fulfilled and your assert will issue a warning or error message. Now you can write more complex assertions. Say you want to write a property. For example, read and write signal both should be valid, read and write, and its negation. So if this condition doesn't hold, this property doesn't hold, your assert will give you error warning. So it will basically constantly keep checking. Okay, keep checking that this read or write should not happen both at the same time, because we have put the negation sign here so that this condition becomes true. If both are true at the same time, then this is 1, this is 0, and this is gonna give you the error. Okay, you can write more complex properties, say at the passage of the clock. Okay, so if the request is asserted, then by using this by using the colon sign in acknowledgement, you're making sure that acknowledgement comes after 1 to 2 clock cycle after your request is being asserted. Okay, now you can write more complex assertions in terms of sequence. If you want to make a sequence, say handshake sequence. So at the rate of at the passage of the clock, request is asserted, and then after that, after request is asserted, between 1 to 2 clock cycles, acknowledgement is asserted. So that becomes your sequence, and then you can call assert a statement, assert property, and your handshake sequence. Easy. These simple 3 kinds of way to define assertions, and you can write these assertions at multiple places wherever you want to write, basically wherever you want. And okay, these are critical cases and I want to write assertions for these critical cases. Good. So thank you guys, this was a very quick overview about system Verilog. I hope you guys have liked it, and don't forget to subscribe LEPROFESSEUR YouTube channel for many more videos, lectures I plan to do. Subscription will help you to notify. And thank you once again for subscribing LEPROFESSEUR YouTube channel, and we appreciate your support. Have a wonderful day.